Hello and welcome. I'm Praveer, and today I'm going to share quantum-driven molecular design using a QUBO approach to optimize functional imprints for material innovation. This is a backup presentation to be delivered at Imperial College London for the IEMRONICS 2025 conference next week, April 3rd to the 5th. In this presentation, it's very brief, but I'm going to first summarize the overall concept, given that it is a new approach, a suggested approach to molecular design using quantum processes. I'm going to draw attention to unorthodox chemical combinations that we know cannot happen chemically, but the idea is that if we were to use quantum processes, maybe we could create a new kind of quote unquote synthetic molecule that had those imprints or the functionality that we wanted to see in that target synthesized molecule. I'll go over the idea of energetic imprints by considering carbon as a representative atom, and then I'll briefly go over the optimization of functional imprints using a QUBO, which is a quadratic unconstrained binary optimization approach. Because if we have a target molecule that we want to create that had a number of energetic imprints, there's many different ways to combine these. And the idea is how can we optimize that design and through creating a QUBO, which is then passed on to a quantum computer. And here I actually did the whole process. So I went through a comparative analysis using D-Wave's quantum computers and used its simulated annealing sampler and also its quantum processing unit to generate different molecular designs given the constraints that I specified. And I'll share that output and then summarize and conclude. So the overall concept is basically to present a novel approach to molecular design, and the QUBO is part of this novel approach. There's a book that I've written that's to be published in June this year by Springer Nature. It's called Pioneering New Avenues in Quantum Technology. And essentially, in that book, I'm proposing using quantum processes and specifically being able to isolate different energetic imprints of elements, for example, carbon, silicon, and so on, and then being able to manipulate those, combine those to create a new target synthesized molecule. And the QUBO approach that I present in this paper is part of that process because before we even engage with hardware and trying to come up with these different synthesized molecules, we would first have to know what the optimized design is. And this is where the approach in this paper is comes in handy. So I can draw an analogy to the idea of genetic engineering, where we have different genes that might combine together or have different imprints. And the idea here is that since we know that there are constraints in bringing together certain kinds of chemicals and combining them, similar to genes, we have functional imprints of these elements that can be thought of as abstract representations of properties. And here I've grouped them broadly into four sets that I call power, service/presence, knowledge, and harmony. The methodology is demonstrated through construction of a QUBO, and that creates a hypothetical, when fed into a quantum computer, it creates a hypothetical synthetic molecule that I'll show the results of. And this QUBO is formulated in Python, and as I said, it's passed on to D-Wave's quantum processing unit. So unorthodox chemical combinations, we can think of many, but just to get us focused here, we know that, for example, helium is traditionally considered inert, and yet there's emerging theoretical work that suggests it can form stable compounds under extreme conditions. For example, we have dilithium helium that, if it were to be created, could potentially pave the way for superfluid-like materials or lightweight superconductors. Similarly, we have diamond-like iron-carbon hybrids that could create ultra-hard compounds with electrical conductivity, or we have boron nitride nanotubes that could exhibit remarkable resilience to radiation, making them ideal for protective coatings in harsh environments and so on. So we can see the utility in being able to create synthesized molecules that it cannot be combined chemically as of now. So using carbon as an example, um, and I use carbon because it's a very versatile element, we know that it has a vast range of properties. So, for example, we have the, say, an energetic property called power that's evident in carbon's ability to form strong bonds, and particularly in its diamond structures. So if we can hypothetically isolate that energetic property of power and then store it in some kind of hardware and then manipulate it or combine it and then program matter to actually have a combination of different such energetic elements, then we have the basis potentially of coming up with a new kind of synthetic molecule using these quantum processes of energetic combination, if you will. And here, what I've done is I've taken the different properties of carbon and just um, categorize them by four broad sets that I call power, knowledge, harmony, and service/presence. And then just generalizing that, assuming we have a large number of elements with many different energetic properties, we can create a much larger set of power, knowledge, harmony, and service/presence that has these different imprints that are part of its elements. And so this becomes the library that we can then use to create these synthetic molecules, which is the idea. But as I mentioned, sometimes if we want a particular set of functional imprints, then we would have to go through some optimization process to be able to create the target synthesized molecule we want. And here it's useful to use a QUBO approach, the quadratic unconstrained binary optimization approach. And in the paper, um, I created a QUBO that was formulated using Python. And essentially, what I tried to do, what I did with this QUBO is set the objectives and constraints for hypothetical synthetic molecule, which had four atoms, and each of these atoms was driven by a primary energetic imprint, but then had a number of different supporting energetic imprints that I wanted embedded in the atoms and then combined into that molecule. So in this QUBO, I specified up to 20 supporting energetic imprints per atom. And then this idea basically generated both the objective and the constraints that were programmed into the QUBO. And here I'll just mention a couple in the interest of time. So there's an intrinsic assignment of a property that is representative of the primary element in the atom. So let's assume that it derives from the set of knowledge. And then there was a random value generated to that property. And then with every additional energetic imprint assigned to that atom, the value of the atom was essentially incremented by the product of its intrinsic value and the added energetic imprint. So that was just the way it was set up. There's many different ways it could be set up. And then this became the objective function. And then similarly, then there were a number of constraints set up, and I'll just go over one constraint. And these constraints were, one constraint was set up so as to ensure that from the library of properties that we have, that there was only one property assigned to exactly one atom. And that was just the way that I set it up. Of course, there's many different ways one can set it up. So as a result, there was a QUBO created, and then this QUBO was then sent to D-Wave's QPU and its simulated annealing sampler. And here I want to share the results I got back from this quantum process. So basically, using the QPU, we can see that the lowest energy was negative 143,000. And in simulated annealing, it was a lower energy of negative 152,000. And so we can see that they were in the ballpark. The total properties assigned to the molecules were 76, and the total sum of secondary property values was 286 versus 382. And the total molecular property value of the optimized molecule, which was surfaced as a result of many different possible combinations, was again in a similar ballpark. And as we look at the constitution of these idealized molecules, we can see that they're different uh, energetic imprints that are assigned. So in this setup, what I actually asked the computer to do, or the way I set up the QUBO, was you had a molecule that had four atoms. Each atom had a primary functional property that derived from one of these four sets that originally was obtained from looking or generalizing the properties of carbon. And then there were a number of different elements from generalizing functional imprints from many different elements, and they were combined together in a unique way. And then the computer was asked to generate the optimal value for the molecule, and this is what it came up with. And these are the actual synthetic molecule that was created as a result. So just summarizing and concluding, this study introduces an important piece of a quantum-based framework for molecular design that hypothetically transcends traditional chemical limitations by harnessing abstract functional imprints. The work was motivated by identification of unconventional chemical combinations, which underscore the need for innovative design strategies. I used an abstraction of carbon's diverse properties and basically created four domains that I call service, power, knowledge, harmony. And that provides a conceptual basis for rethinking molecular construction. As I mentioned, that abstraction was generalized to encompass a wider range of elemental properties. And I then created a QUBO to create a synthetic molecule which had four atoms with different primary functional properties and then a unique set of energetic imprints attached to each of those atoms. And this was from a set of 20 different possibilities. And then I asked the computer to come up with the basic molecular design that would maximize the value of those functions, the energetic imprints, where there was a randomly generated value assigned to that energetic imprint. Of course, if you were to do this, taking the next step, then it would be based on the goal of the molecule and basically the energetic imprints that would then fortify that goal that we had in mind. Comparative experiments were conducted using D-Wave's QPU and classical simulated annealing, which revealed basically functional molecules characterized by four atoms with different energetic imprints. There were two different optimized molecules that each process generated. And the value of that molecule, given the constraints and the objective that I had set up, was similar, was in the ballpark, but yet the simulated annealing approach appeared to have created a molecule of a higher value. And this I'm proposing finally is building on the backup technology envisioned to isolate and leverage energetic imprints. So somewhat like combining different genes together. And again, the QUBO approach is seen as instrumental or an important part of a process of coming up with some kind of synthetic molecule which can be programmed into matter. Thank you.